Hello everybody, welcome to our session today that's looking at physics in the spotlight, and this session is on physics to save a life. We're celebrating British Science Week this week. Our focus is very much on physics, which you'll guess from the title, and this is because we're being funded by the Ogden Trust, who support and promote careers in physics. So thank you very much for coming along today. We have three speakers from different fields within the wider kind of health sector. Looking forward to hearing what they have to say. We'll be introducing them in just a minute. But before we do, a little bit of housekeeping from us here at Founders for Schools. So you're all off camera and all off mute. That doesn't mean to say we don't want to hear from you though. If you have any questions, please do pop them in the chat. We're going to hear from each of the speakers first, and they'll learn a little bit about what they do and how they got there. But once we've done that, we will open it up to questions and answers from the group, and you can find out what you want to know about their careers and how they got into it. So now that that's all sorted, thank you, three of you, for coming along to talk to us today. Absolute pleasure to have you with us. We're going to start with Lamise. Lamise, if you'd like to tell us a little bit about what it is you do and who you do it for and how you got there and how physics plays as part of what you do.
Absolutely. Thank you very much, Alison. I'm just going to share my screen. Let me know if you have any problems. Can you see that?
It's getting there. Yep. Yes.
Okay. Okay, so hello everyone. My name is Lamise Montero Sharat. I'm a therapeutic radiographer and I'm employed by the Maidstone and Tunbridge Wells NHS Trust. But of course, my role requires me to travel across two different sites, one in Canterbury and one in Maidstone, and that's both located in Kent. So what do we actually do? Therapeutic radiographers, what we do is we use ionizing radiation to treat patients with cancer. And because, as we know, radiation is harmful, mostly, especially to those who don't need it. That's where we come along. So we are responsible for accurately planning and delivering this radiation treatment so that we ensure that at least 95% of the dose is given to the cancerous tumor, while very minimal dose is given to the normal surrounding area. This usually involves high energy X-rays, which is produced via what is called a linear accelerator. I'll show you the next slide. So the big machine on the right, that is the linear accelerator, and the person lying on the couch, that is the patient. And inside the patient, you can see there's a tumor that we're trying to treat, the red bit in the middle. Unfortunately, it is obviously inevitable for normal structures to also receive some radiation dose. And therefore, therapeutic radiographers are also trained to manage side effects brought on by the radiation by giving appropriate advice to patients. As you progress into your career, you will be given opportunities to further enhance your skills, where you are at some point able to prescribe certain medication to alleviate some of the side effects. So what skills do we use for our role? Being a therapeutic radiographer requires several skills, as you can imagine. Some, of course, are developed at school, but as you go along with time, you progress and you develop a bit more skills. From my experience, I can definitely say strong communication skills are at the forefront, because not only are we required to accurately communicate with and relate to a diverse group of patients and their carers of varying ages, backgrounds, and needs, but of course we have to communicate to our colleagues within our team and alongside the wider multidisciplinary team. And of course, as I said before, working within a team is important, but at the same time, it's also important to be able to work autonomously at times, with certain tasks. It's also very important to be able to build a close trusting relationship with patients, giving support, reassurance, and explanations over the course of treatment. Because the treatment can last up to maybe 7 or 8 weeks, where the patient comes in for their treatment every single day to have their treatment, which takes about 15 minutes. And then they go back home and they come back the next day. So, of course, that allows us to be able to build that relationship. You also have to be confident to be able to have the ability to work with complex, highly technologically advanced equipment. This is what it looks like while we're training our students. We are then able to, of course, give them an idea of what it's like to manipulate a linear accelerator without having a patient on it, to be able to train them at first. Good organization skills and time management skills are important to plan and treat patients in a timely manner. And of course, in this profession, you will need a willingness to keep up to date with changes in technology, like attending courses and reading journal articles as part of our CPD program. So how did I get where I am today? Our degree is a 3-year undergraduate degree, but because I did mine in South Africa, my degree was a 4-year honors degree in radiotherapy in Cape Town, South Africa. As part of our program, we had to also complete 2 years of community service, and that I did in a different city, which was very instrumental to my learning because I got to learn different cultures in that city, even though it was in the same country. I was then afforded the opportunity to work in Abu Dhabi in the United Arab Emirates, where I worked as a senior for about 4 years before moving to the UK and settled up in Kent. I started my career in Kent as a therapeutic radiographer, and I quickly grew to enjoy supporting and training undergraduate students, and completed a postgraduate certificate in higher education. And that's how I became a practice educator, which is a clinical lecturer, basically in clinical settings. So we don't go to a university as such, but we do a lot of support and training to students within our department in order to assist them in completing particular clinical competencies, which is necessary for their degree. So at the moment, in addition to supporting students, I also facilitate new staff because, of course, they are still transitioning from their student into a qualified staff, and that takes a lot of courage. So I support them with that as well. So how has physics helped me to get to where I am today? Physics at secondary school has certainly played a role in my career. It gave me the building blocks which I needed to branch into a very specific area of science called radiation physics. Our training at university enabled us to understand how radiation is produced, firstly, and also how it interacts and attenuates with different organs and tissues within the body. And by grasping these concepts, we are empowered to derive mechanisms by which we can actually manipulate the radiation beam to do what we want it to do, obviously, which is to deliver radiation to the tumor and avoid critical normal structures which are surrounding the tumor. But in order to accomplish this, we need to understand the theory and principles underlining these concepts. Physics also helps us to decide. They help us to decide and understand exactly how much dose is needed to kill a specific tumor and over what length of time it is needed, how many days, so that normal structures are given a chance to recover, while of course the cancer is not. So what skills are involved in your job, especially those that physics help to develop? I can certainly say that when planning a patient's treatment, we often have to problem solve. We have to refer back to our knowledge of physics to remind ourselves of what the radiation beam will do when it goes through different organs, such as what it will do when it goes through the lungs, as opposed to what it will do when it goes through the bones, and then make decisions appropriately. It gives us the confidence actually to construct logical arguments to complex problems so that we are equipped to justify our actions that I take to ensure patients get the best treatment with minimal side effects. It also enables us to understand the wider implications of decisions made based on theoretical concepts, and now my experience in this field also contributes to the skill. Finally, numeracy, computing, and research skills are certainly required to ensure that patients are accurately treated, and that as a profession, we continue to progress to improve the lives of cancer patients undergoing radiotherapy. I'm just going to take you to my last slide. I just wanted to show you an example of what it looks like when a patient is undergoing radiotherapy as a treatment modality. You can see the lasers, the green lasers, that actually helps us to position the patient so that they are in the correct position every single day. And the little head on top of the machine, that is where the radiation actually comes out of. And finally, I've just got some further information. Anyone who has needs any further information regarding radiotherapy or a career as a therapeutic radiographer, please don't hesitate to get in touch. There's a few websites that might give you a start. And of course, the Society and College of Radiographers is also a good place to start. Thank you very much. Thank you, everyone, for your time.
Great. Thank you very much for that. That was really quite interesting. Lots of what looks like very, very cool tech.
Very much so. Thank you.
Great. So we'll just hear from some of the other speakers, then we'll come back to some questions. So Francisco, can you please shed a little light on what you do as part of your job, please?
Well, thank you, Alison. Yes, let me first share my screen. Let me know when you can see.
We can see it. That's great.
Oh, sorry. Okay. Well, first of all, let me introduce myself. My name is Dr. Francisco Cabrera, and I'm a Marie Curie Research Fellow at the City University, working in photovoltaic solar cells. A little bit of background about myself. I started my academic career by being simply an undergraduate student. I first of all did a BEng honors in electrical and electronic engineering, specialized in communications. Then I moved on to doing a Master of Science in Telecommunications and Networks. I was able to get a PhD studentship, and I did a PhD in photonics. I specialize in photovoltaic solar cells for optical simulations. And then I moved on for a few years to the industry, and I was able to come back to the academia as a Marie Curie postdoctoral fellow at the City University. So in general, what does a researcher do? You may ask yourself. What the thing that we are doing, we are always trying to find a solution or an improvement for a given problem. For that, what we need to do is to think outside the box by applying basic principles given by physics. Apply a little bit of common sense, which sometimes is it's something not so commonly used, but it can be very useful. And then also what we need to do is constant learning. We have to keep on reading books, we have to keep on reading journals, attend conferences, and also attend some courses. And then by attending those courses and those conferences, we are able to meet some other researchers and create a network of collaborators, and then we can all together try to move and develop the field in which we work. And then in particular, what do I do? My target is to minimize reflection from the solar cell surface by to maximize the absorption, because when you have when the light is incident on the solar cell surface, there is a big portion of the light that gets reflected. So my target is to minimize that so that we can maximize the absorption. And I do that by applying a concept which is called light trapping. That sounds very fancy, but what does it mean? In the case of a planar solar cell, you have the incoming light that hits on the solar cell surface, planar, so it's a flat surface, and then the light is incident only once. But if we have a solar cell which is textured, as in this case, we can the incoming light is going to hit once, twice, and then it depends on the height of of these elements. We can get even more times, and then we are going to get the light absorbed. So we are going to get an amount of the light absorbed at each of the times that the light is incident. So we are, by doing that, we are effectively trapping the light, and we are enhancing absorption of light as well. And now to try just to give you a little sense of the implication of all of this, I have prepared a video out of a simulation to illustrate the meaning of this. So in the case of the planar solar cell, when the light is incident, you have the light which is incident and then simply hits the surface. Some of it gets absorbed, some of it gets reflected, and then that's it. But now when we do that in the case of the texture solar cell, the light is coming down, and already you can see some interaction there. Gets the heat is incident on the surface, and then you can see all this interaction of the light, indicating that the light has been effectively trapped, and then we can optimize the absorption, which is what we're looking for. And then that's it. I thank you very much for your time, and then I am looking forward to answering all those questions.
Fantastic. If you just want to close your presentation down then, Francisco.
Yes. Stop.
Oh, there we go. Excellent. So thank you. That was a nice insight into when we say saving life, maybe kind of a wider, this is what we want to do with the planet and make sure everything is there and existing for us in the many, many years to come. Obviously with the climate change and the net zero, there's real issues, particularly in certain parts of the world where that sort of technology can really be life-saving. So thank you very much for that. That was fantastic. But that takes us to our last speaker, Katie Lou, who's going to tell us a little bit about what she does. And then once we've done that, if you've got any questions, pop them in the chat box and we'll start asking our speakers. Okay, when you go, Katie.
Can you all see my screen all right?
Yes.
Yes.
Wonderful. So I'm Katie Lou. I'm a medical physics PhD, so I'm earlier in my career than both the other presenters. And I'll tell you a little bit about what a PhD is and what I do in my PhD. So first of all, what is a PhD? So it's a 3 to 4 year research project where I'm employed by an academic institution. So for me, that's the University of Cambridge. And then you're tackling a problem that doesn't have any solutions yet. There's quite a bit of overlap with the previous PowerPoint actually regarding this. So how do you tackle an unsolved research problem? Well, first you ask a lot of questions. What is the problem? What am I trying to address? And what's been done already? And so what needs to be done next? Where do I fit in? And once you have read around on what's been done so far and you've got an idea of what you want to do to tackle it, then you need to test these new ideas. You do experiments. sometimes they'll work, sometimes they won't, and you will go around and you will redesign your experiments, and all the while you'll keep reading and learning new skills, staying up to date on what everybody else that's tackling similar problems is doing in the field. And similarly, you have to communicate. While you're reading what everybody else is doing in the field, you have to tell everybody else what you're doing. And you'll do this through publishing results in academic journals and papers, or telling people in presentations at conferences, and even doing outreach. You'll be telling the future generation where we're currently at, so that then that research can continue to progress for years to come. And then at the end of a PhD, you summarize everything that you did in those 3 to 4 years in a thesis, which is basically just a book summarizing everything that you did. There's lots of different types of PhD, lots of different group sizes. So I thought I'd just show you mine. So I've got quite a big research group, and everybody who's got red around their name is a physicist. Everyone who's got blue is a biologist or similar. And then the two with black around their name are computer scientists, and we've got our boss in the middle. Now, we're all cancer researchers, and there's a lot of physicists here. But even then, the lines all get very blurry once you get into research science. And when you see the project, you'll probably see why. So I designed multispectral endoscopes for early cancer detection. I'm going to break that down for you. So sometimes cancer can appear as a surprise, but sometimes it can be the end result of a progression of disease. And so the cancer that I work on is a cancer at the bottom of the esophagus. And it often comes at the end result of a progression from something called Barrett's esophagus. Now, Barrett's is where the bottom of your esophagus, esophagus being your food pipe, becomes burned by stomach acid that has escaped upwards. Now, Barrett's esophagus itself is benign. A lot of people have it without ever developing cancer. But what that Barrett's can do is it can develop to something called dysplasia. Now, dysplasia just means badly formed, but we say it in Greek so that we sound more impressive. But dysplasia can go from low grade to high grade, and the likelihood of developing low grade dysplasia is quite low. But once you have low grade dysplasia, the likelihood of developing high grade dysplasia is higher. And once you have high grade dysplasia, the likelihood of then developing cancer is even higher. So it accelerates through this progression. So it's really important to try and identify it early. If you can spot it when it's low grade dysplasia, you can actually just remove it during an endoscopy. Endoscopy being a camera on a tube that goes down your throat and has a little look around. So you can remove it there and then, and it doesn't have the chance to develop cancer. Problem is, it's really hard to see. So what we've got here in this picture, sorry, I probably should have given you a content warning on that one, is the pale colour is the healthy esophagus that's all flat, and the red is Barrett's esophagus. Now here is where we've got some low-grade dysplasia, and even when you zoom right in, it's quite hard to tell it apart from the background. And the reason for that is that we make cameras that imitate human vision. And human vision's not very good. For example, here we've got 4 sets of pairs of colours, and they're all separated by the same wavelength difference. But there are some that we find much easier to tell apart than others. And that's because we only see 3 colours, red, green and blue. And then we fill in the gaps according to what we've seen. And that means that we find some colours easier to tell apart than others. So we then make cameras to try and imitate this vision, but we can make cameras that can see better. So a previous study in my lab took a spectrometer, which measures all of the colours that are reflected, and they sent it down an endoscope to see what different colours are reflected off those different tissue types that we're trying to tell the difference between. So these are the spectra of that healthy tissue, that Barrett's that's not a problem, and that low-grade dysplasia that you want to find. And as well as having those wavelengths on the bottom, I thought I'd give you the corresponding colours, so it's something slightly more meaningful. Now, when we think of that red, green and blue that we can see, we just don't have enough information from those colours that we can see with a normal camera and with our eyes to tell the difference. Now, what you can do is you can use multispectral cameras, multispectral being lots of colours, to see that colour difference in more detail by breaking down the image into lots of small colour bands. And a nice example from this actually comes from space. So this is an image from NASA of the sun. And each of those triangles is this same image of the sun seen at different wavelengths. Now, as it goes round, you'll notice some features that are very obvious in some colours and very invisible in others. That's what we're trying to achieve in the esophagus. There's a couple of ways to do this. So a regular camera will have colour filters over a sensor that's sensitive to light. And then when we've got an endoscope, we're also controlling all of the light that's going to be going in. So we could not have a filter array, just have a blank sensor, and then shine different colours of light and take images one after the other. And so these are two options for building up a multispectral image of the inside of an esophagus. Now, what I do is I make these filter arrays. So I use some the physics of light and waves to make simple colour filters. If you have two mirrors very, very close together, and by very close, we're talking nanometers, so around the same scale as the actual size of a wavelength, then you can essentially trap light, but like we were seeing before, but you only trap light of a certain colour, and only the light that's trapped can make it all the way through. So you selectively let a particular narrow group of wavelengths through your filter. And so I fabricate these very, very tiny filters. And because they're very, very tiny, I have to cover every part of me. There's a little picture of me in the clean room in order to not get any dust in them while I'm making them. And so you can see on the left-hand side is the design and the concept with the filter arrays. Then at the bottom is an actual picture of one of the little chips that I've been testing. Of these wafers here are when I was just making them on some glass so that I could see through them as well without having to take any images with the sensor. What we have on the right-hand side is me having a look at what these filters look like through a microscope when lighting them from above and lighting them from below. So I can see that my colour filtering has worked. And atomic force microscopy, that is, again, some great physics, but essentially just seeing how tall all of my different filters are in order to see how this height is corresponding to the colour that they're filtering. So then once I've made these, I have to test them. So did I make them correctly? Are they filtering the right colours? And I can use a spectrometer again for that. And then I wire them up and I take photos with them and just see how good are the photos that they're taking. Meanwhile, so yeah, once I've taken my images, I have to then process them. So when I have a photo that's taken with all of these grids of different filters, it'll look like this, where there's a whole grid of coloured squares, and that doesn't look like a photo yet. So what I do is I separate them out, fill in the gaps, and then add them back together. That's what your phone camera is doing in real time all the time. But because I've got lots more than just this red, green, and blue, I have to write my own code and do quite a lot more computer processing myself in order to make these images happen. Meanwhile, we're doing that thing where we're varying the color that we're illuminating with in order to gather more information from real patients, because we can't just stick my homemade cameras straight in somebody. That would be dangerous. So in the meantime, whilst I'm developing the new cameras, we're also getting more information from real patients in order to make sure that the cameras we make are most effective. So how did I get here? I'm not going to spend too long on it, but I just thought I'd summarize subjects that are more relevant to you guys at this point while you're at school. So I picked my GCSEs out of a hat because it was a hard decision to make. But I also realized that if I'd have picked one out of the hat that I didn't like, I'd have realized. And I did astronomy as an extra GCSE because I just thought it was cool. And then I thought, rather than just breaking these down into subjects, also breaking them down into skills. Because there are a lot of skills from subjects that I don't do anymore that still pay forwards in what I do now. I also have included things like Maths Challenge, Physics Olympiad. I don't know if you guys have come across these. It depends where you are as to whether you have like seen them, but some of them you can just sign up yourself. And they're a lot of fun because they're very low stakes. They're very fun problem solving that I learned a lot from. And if you do a maths challenge and you don't do very well, then you just ignore it. So it's a great way to gain skills at very low stakes that have actually paid forwards a lot, because there's a lot of out of the box thinking that doesn't require memorizing anything, which I'm not as good at. And then when I came to university, I did natural sciences, because just like I picked my GCSEs out of the hat, sometimes decision making is hard. And so I chose a degree where I could stay interdisciplinary and not choose one particular science. And that's actually been really useful for what I do now, because I am doing physics, but I cross over into so many different disciplines within my research, and any researcher will tell you that that's quite standard, is that the lines get very blurry at this point. So I was able to specialize in sort of biophysics and medical physics, and this is now very useful in what I do. I also, whilst I was in my first year, applied for a student sponsorship, which is something that I don't think is always very well advertised, but was very, very useful. So I did, I got sponsored throughout the rest of my undergrad degree, but also did internships in MRI magnet manufacture, which I'm happy to talk about in the Q&A, but I've not got any won't go into detail now on. And yeah, I'd say look out for these. They didn't even it wasn't a sponsorship where they required me to work for them at the end. So it was all benefit really. But what's next? So got these clinical trials and I'm making my new devices, and it's really important to tell people throughout your PhD what you're doing and keep people up to date. So that's the short term. In the long term, I thought it'd be nice to just see where you can go from a physics PhD, which is pretty much anywhere that you want to go. The doors are all open. And if you want to sort of see what opportunities there are, and also make sure that you are connected with people for your next step, I've just included a little reference to LinkedIn and Workfinder. So LinkedIn, I think you've probably heard of. Workfinder is a Founders for Schools initiative, which is similar. Alison can probably tell you a little bit more about that in the Q&A, because all the way along your journey, you will meet lots of people who you might want to speak to again later down in your career when your career moves and develops. And that is all from me for now until the Q&A.
Thank you, and thank you very much for that little plug for Workfinder. Yes, indeed, if anybody is ever looking for any sort of work experience or internships, Workfinder is a very useful resource. You can go on and sign up for free, and lots of companies post opportunities that they have there. Hopefully something will work for you. So thank you very much, all three of you. What I really liked was there was a very common thread about learning, I have to say. You all seem to have taken multiple opportunities to go back and learn different skills, and clearly there's research that's very common thread through all of what you do as well. And some of you talked about some of the skills that you need in your job, and I just wondered if you were to give advice to a young person who's still at school, what sort of top 2 or 3 skills do you think they should focus on trying to develop that will help them if they go forward in your sort of career? And I'm thinking about transferable skills here. What would be helpful for them to really make sure that they understand what it is and can talk about it to future employers or future universities or colleges to say, I can do this? What do you think? We'll start with you, Lamise. What do you think?
Alison, I think for me, a key skill that I feel is sort of really important is just communication skills. And I think that you can sort of develop, as you go along. So I was never really good in like written communication, but as you progress through your career, you realize just how important that is. And I think that sort of starts off at secondary school, communication via, verbally, orally, like I said, written. Another skill that I always find is quite useful is just developing your troubleshooting skills, because there's always problems, and you don't really have to wait for someone to come along with a solution. Try and think on your feet, do some research. There's a lot of resources out there that can help you with those problem solving skills, and that comes along every single day. So take advantage of those and try and make the most of it, really.
I mean, based on what both Francisco and Katie Lou, you said in your presentation, I think you would maybe agree with that. Is there any other skills that you think they're really key that you wish you'd maybe paid a little bit more attention to it in school?
Yes. Well, let me first input something. I think something that could be very useful, probably something that the teachers and probably even the parents, they keep on telling them. It's about planning, management of the time. Sometimes you don't realize how important that is. You only realize it once you need it. So that's something very, very useful. Try to get a good habit of about managing time, and also as Yami just mentioned, troubleshooting. That's incredibly valuable. Just with even if it's just in your daily life, you just find instant solutions for easy problems. Then you can replicate those once you are in your within your career, and then you will be able to get yourself out of trouble, which happens very often, and then you will thank yourself later on. So
when we say trouble, we don't mean serious trouble. We just mean little.
no. Yes.
Just
I think
excellent. What about you, Katie Lou?
I think when you said something that you maybe wish you'd paid more attention to, I think coding and computer skills was something that I didn't develop as much during my time at school compared to other problem solving skills. And now that I am a researcher, they're vital. And I've picked them up along the way. And certainly when I did my remote internship that I mentioned briefly, that was all coding based, and I essentially learned on the job, which is certainly it's a way that most people do it. But I think there are lots of resources out there and like hackathons, events like that, where you can actually have a really good time learning to code before it's essential for your job, which I think is actually an opportunity to learn it in a really fun way whilst you're at school. And that is a transferable skill that will certainly be a huge benefit throughout your future career.
I will second that. We talked to a lot of tech companies and companies that need people with strong digital skills. So yes, that is a very sellable skill to have. Okay, we do have a question from Avanti House Secondary. When you were at school, did you already know what you wanted to do? Well, I look as though we were getting a nod there from Louise.
I think I'm one of the few people, Alison, that I sort of knew exactly what I wanted to do, from when I was 16. I know that's strange, but it did come from a life experience, because I had a very close family member that had cancer and died from cancer. And I think that prompted me to get involved. It's something, to help with cancer patients as such. And she needed radiotherapy. And at the time in South Africa, I don't think radiotherapy was well known. So that prompted me to go into it. And I quickly realized that that's what I needed to do. And I think it's really nice to have just like a goal, because that sort of really set me off. I was sort of a very average student at school. And I think the minute I realized that that's what I want to do, I just did it, and you just happen to do well because it's something you have passion about.
Excellent.
I don't think it depends when you say what you want to do. I didn't come out thinking I want to make endoscopes for seeing cancer, but I'd say I asked myself 3 questions. What are you good at? What do you want to achieve? And what do you want your work day to look like? So what was I good at? Well, I enjoyed problem solving and maths and physics, and I wanted to have a net positive on society, and I wanted to have my workday being something where I could continue to be curious and explore. And so by doing this like PhD, I'm getting to be curious and explore and use my skills to help people. When I was in school, I was considering the sort of the spectrum of like fundamental science versus something more applied like engineering or medicine. And I'm somewhere in between, because I realized that this is where my skills will make me most useful. And if I had been like, well, I really like maths and physics, but I have to help people, therefore I will do medicine, actually, I would have probably been less effective with my skill set.
Yeah, so a bit of self-awareness and just knowing yourself, important. Good. What about you, Francisco?
Yes, well, in my case, I didn't know exactly that I wanted to end up doing research in photovoltaic solar cells, but I did know that I wanted to do something in physics, because when I was in secondary school, I had a brilliant teacher for my physics, and then he sparked a curiosity inside myself, and then I was able to just with my own passion for the field to keep moving, to keep on trying to learn. Then I knew it was something about physics. I knew it was something about the optics. I by that time I remember I liked a lot optical fibers, and then I was all the time curious, trying to learn more. And then when I did my BH and then I finished it, I remember thinking, I want to learn more. So I move on to doing the Master of Science, and there I had the option to move on to the PhD, and I still want to learn more. So it's always that curiosity. That's what's going to lead you the way. So whether you may have some general idea about what you want to do, you may if you're lucky, you know exactly what you want to do. But you will always have some sense roughly what you want to achieve, and then simply your own experience, your own life is going to lead you to the right path.
Fantastic, good. Now, based on that, then I think that's a nice lead into a question we often ask our speakers, and that is, if you had to give yourself, your 16-year-old self, a bit of advice, knowing what you do now, what advice would you give yourself? Lots of pausing phases. I think, Katie Lee, you might be coming to an answer first.
Well, I think the coding thing that I already said, thinking about what I do now, advice that I've given friends at decision points as well would be, do something that you enjoy and it will take you to somewhere that you enjoy, even if you don't necessarily see where that is yet, which is perhaps a little vague, but has so far proven quite good advice.
So I think that's helpful, because you didn't use the passion word, which sometimes I think young people can struggle with, because they're like, I don't feel passionate about anything, but enjoying, that's different. Hopefully they have something there. What about you, Lamise?
I sort of feel like perhaps I should have been exposed to a bit more, taken myself out to different industries, like Workfinder would have been amazing. Like Francesca said, based on your circumstances. Obviously, at the time, I didn't have that option, but I think I should have made a better effort to just reach out to companies and just find out who offered work experience. But yeah, anyway, I think that would be a good start.
Excellent. Okay, and Francisco?
Yes, now the advice would have been just enjoy the time, enjoy what you do. Try to try to make friends on the way, which also can be helpful, and then always give a good impression to others. It's some very tiny little detail can make a long way later on. Always give a good impression. Also, probably I would have done more about the communication skills because after I have done a lot of presentation, and for me initially it was very difficult. With time, I improve a little bit. So yeah, those factors I would say.
I have thought of one more that as
Okay.
well is don't be put off by rejection. Send out all the applications and don't take it to heart if some of them come back with nothing. I remember I really struggled to get work experience when I was 16. Like I tried some like research places, absolutely nothing. Someone thought I was signing up for a clinical trial. I was like, we've had a miscommunication here. I even got rejected by the local bakery once I was like, okay, no science, I just want something, nothing. But then eventually, because I'd clearly put the effort into trying to get something and just drawn lots of bad luck, one of the teachers took pity on me and managed to put me in touch with a parent, and then I managed to get medical work experience, which was much cooler than what I'd originally even set my sights on. So
Excellent. Well, I think that's a good note to turn on. Don't be afraid to finish on. Don't be afraid of rejection and reach out to as many people as possible. Thank you very much, all three of you, for coming along and talking today and sharing a little bit about your career journey. It's been really interesting listening to you. You all have what sounds like really interesting jobs, so thank you for that. Thank you as well to our sponsors, the Ogden Trust today, for helping us put this on. And to everybody else, thank you very much for coming along. We will be sharing the recording afterwards if you want to take a look back and maybe share it with a wider group. Have a lovely British Science Week. Let's hope you're doing lots of activities to find out about lots of the many, many different jobs and careers available to you in science. Great. Thank you very much, everybody.
Thank you.
Bye-bye.
Bye-bye. Thank you.